Okay, we are now live on YouTube as well. We basically stream this presentation immediately onto YouTube, so everything gets recorded there. So there is no work for me afterwards to do it. But let me start sharing my screen. Let's do it this way. Share. Okay. After last week's discussion, there was Peter Rowland made a very important point, and basically he brought. He said if we start with any of my three vectors that I had, we will have a Maxwellian type of solution. So that's why I now renamed this to a general Maxwellian dynamics. This is basically, there was also the slide I started last week's, with basically waves are the only equation we know that represent waves is the D'Alembert wave equation, which we can see in the one-dimensional and in the three-dimensional form on this slide. If I now draw the vectors of a single plane of an electromagnetic wave that is propagating, shown by the propagation vector u, magnetic vector, field vector b, and the electric field vector e, and a position vector p, I then can write these three equations that E equals u cross b, u equals 1 over b squared b cross e, and b equals 1 over u squared e cross u. These equations are basically are the Maxwell equations in vector algebraic form. They are the Maxwell equations if we take the, which is very easy to do, if we take the left-hand, right-hand curl operation. So if we look at what is curl E equals curl U cross B, which is here, which develops into four terms. It's basically the vector algebra, the back-cab rule, which are the first two terms. But because it's the nabla, or the curl, is a differentiation, we get these two extra terms that come behind it. This is you'll find these equations in any vector analytical textbook. Now, evaluating these equations, we see that the divergence of u, the divergence of b, and the divergence of e are all 0, because we define u, b, and t and e as functions of time only. And the
mute if you want.
B dot, the dot product of B nabla times U develops into this. We also see equals 0. And now the question is what the last two are. What is what does U, the dot product of U dot nabla develop into? And that develops into a dt, because if we expand it, we got dx dt equal times ddx, dy dt, dy, and we can see that the ddx cancels out, so it just leaves us with a partial ddt. Therefore, the curl of u cross b equals minus db dt, and the curl of e cross u is the partial d over partial t. And if we express it this way from where we started, we now have the Maxwell equations as we know it, and we already showed earlier that the gradient of B and the gradient of E are equal to 0. In the last presentation, I showed I derived the terms epsilon 0, mu 0. Now, instead of, so basically, these three equations here are, because from the Maxwell equations we get to the D'Alembert wave equation, meaning that these equations are also a wave equation, because I can express the velocity vector as a function of t. Well, all these vectors are functions of t, and they can have sine omegas in them, and therefore they are a wave. This is the general or the classical interpretation of the electromagnetic plane wave. This is basically taken out of any textbook. We will note here that the vectors B and E are transposed. That was a choice of our early researchers. I've shown in my paper that it can also be the other way around. It was just an arbitrary choice. So it could, the E and the B can easily be transposed, and the derivation of the classic interpretation of an electromagnetic plane wave remains. Now, I'm going to introduce a new wave type, which I call a rotary wave. Now, think in terms of a propeller, or rather a one-bladed propeller. A propeller rotating in the XY plane, and at the same time propagating along the Z direction. It is very easy to show that that motion can be represented by the D'Alembert wave equation. Therefore, this propeller wave or rotary wave, which I call it, is derivable by mathematics. The other alternative that I do, I replace the magnetic field B with an activation, and call the electric field with a reactivation vectors, or fluxes rather, activation flux vector and a reactivation flux vector. I've also toying with the term of a fluxor to introduce that. I haven't done that yet. You know, instead of a vector, call it the fluxor. They could be, I've basically taken, used these symbols A and R, because in my opinion, these would be the real magnetic and electric, it's not fields or rather activations. So it's, but let's just keep it at A and R at the moment. So basically, if I look at the Maxwellian form of a rotary wave, I have exactly the same as the wave, the Maxwell equations, but just using different vectors here. And then I parameterize it as U propagating into the Z direction. A, we can now see, is a vector rotating in the XY plane, and R also rotating in the XY plane, but with 90%, oh no, not 90%, 90 degrees transposed. And these are a solution to these three equations that you see on the top there. So what does this look like? If we now we have the A and R rotating. I'm showing three positions of the same wave. So it's at position t equals 1, at position t equals 2, and at position t equals 3, or we can think of it as three different rotary waves. But a rotary wave only exists at the point CT along the z-axis in this case. It is not a traveling plane wave. There is nothing behind it or nothing before it. In other words, should this hit you, it would be an impulse. So now I'll make two assertions, or basically, in my last presentation, I made two assertions that the elementary EM wave exhibits power h over t squared, and the elementary wave transports an electric charge E every 1 second, which is a wave current. That was the assertions that I made last time. Now, but for this time, I now change my assertions. But very similar, that a elementary rotary wave R has an action H. This requires A to be an elementary activation flux vector, and the elementary rotary wave transports an elementary load L. I used the what would you call it, the script form of an L, so it looks very much like an E, but it is not the electric charge E. It is, I call it the load. We need to give it some units, and I propose a unit L for this, calling it the Leyden, honoring the Leyden jar, which was first basically used by the early, what would it be, 18th century, or would it be 19th century scientists trying to get doing experiments with static electricity. With this, I have here in bracket, I'm already hinting here that the electron is not the carrier of electric charge that drives our industry. You know, the electron has an elementary electrostatic charge, but it is not the charge that forms a current that lights our light bulbs. And I can actually show you a thought experiment in that respect. But I haven't got it in these slides, but I can pull it up later if you're interested in it. So basically repeating these equations again. So we've got the rotary wave as we discussed earlier. It's basically, if we look at A, I've got here R, which is a unitless constant. L0 is a elementary length. And A is a elementary activation. I'm working here in quantized, so basically L0 is a quantized unit and A is a quantized unit. R, it can be any value here. Again, I say that we've one of our equations is U equals 1 over A, the norm of A squared, A cross R. And on the premise that A cross I is indicative of wave action, we multiply the left and right hand side and substituting that I had here R. We now consider R equals 1 because we're working in a quantized unit. So it's basically, that's why it's omitted here. And we can change this, that U equals 1 over norm A of A or squared A cross R. We can write it as H equals H over L0 squared A squared times C. And the product of the norms of A and R, of the vectors A and R. If anybody wants to interrupt me, if they don't understand what I'm saying here, please do so. Now, action is defined as momentum times distance. Similarly, this is something that I haven't seen in any textbooks. Maybe somebody could correct me here. Rotary action is rotary momentum times the angle theta subtended. That is, the S is generally used for to describe action. So therefore, the rotary action is I, which is a moment of inertia, omega, the radial frequency, and the theta that it extended. I omega would be the rotary momentum, and theta is the angle subtended. Hence, we can formulate quantized rotational action as rho h. Rho here is basically just being used as a unit conversion because I haven't got kilograms in the right-hand part of this equation, and H has got kilograms in it, or rather joules. Therefore, I have some form of a coupling constant K, my load. The moment of inertia, or rather L, that's the load times the unit distance squared, the L0 squared, is basically the moment of inertia. Omega 0 is the radial frequency, and the theta subtended. And here K is a dimensionless proportionality constant of unknown value, which scales the rest so that the rotary action, so that phi, or rather rho, equals 1 Leyden per kilogram, which basically is the conversion needed here to keep all the units constant. Also, in a quantized system with when the angle subtended by theta equals 1 radian, I can that is the same. I can express the rotary action as because you see, I myself getting confused here. Okay, I can convert this if I have L0 is the speed of light divided by the quantum frequency of which would be 1. So that is, and we obtain that omega 0 is 2 pi c over L. Hence, we get this expression. And because the load is carried by A, I can also say that the rotary action is simply L0A times the angle subtended as this, where x is any part of a constant to be determined. This is exactly the same method that I used last time. So if you don't understand, I haven't done anything fancy here, in my opinion. Therefore, I can say that the rotary action 2 pi K times the load times the L0 C theta equals to L0 A theta. And thus we get that A, if we to be 2 pi K load times C over a chi. Chi is some or other constant which that we need to make the top equation to be equal. And using above, so if I use this, replace, we had this equation earlier, and we replace this part here. Does my cursor show on your screens, by the way?
Yeah, it's there.
Yeah, okay. So if the norm of A is 2 pi K L0 load C over chi, and that I replace this part here, which then to give me this equation, which I repeat here. But the norm of R is simply the speed of light, L0A, which I then can bring in here, and I bring in a new, develop two constants here, H over L0 squared, A squared over C, L0 squared over chi, 2 pi K L load C squared A. And now from we are now in a position to define a quantized activator as H over 2 pi KL, which is basically, so it's A, I see, if you look here, we've got A there, H there, and then 2 pi KL, leaving the C. Okay, here it is explained. And basically, I can say that A equals, can I just go back here? I've got this twice here. I didn't realize. So basically, I have developed that A equals H over 2 pi K times the load, which means that this has to be 1. I've now basically replaced it in there, and I come to the conclusion that I have a epsilon dot and a mu dot instead of an epsilon 0 and a mu 0. This was exactly the same what I'd done the last time, except that I have it in a different form. The product of these two, we see everything cancels out other than the C's in the divisors, so that epsilon dot, the product of epsilon dot mu dot is equal 1 over C squared. So it's basically very similar to what we know from electromagnetics. Therefore, if we go now back to our 3 equations, I have a rotary wave that is parameterized by this. So basically, any solution of the unit vectors of the unit vector of R and the equals cross product of the unit vector of u cross A, and similar with the other three equations there. So any solutions of this would be a rotary wave, and one way or the solutions that I know of are basically obtained by Euler rotation, and each particular a particular roton type. Therefore, we have the 1D roton, which is the propeller, which I've shown in the top. We have a two-dimensional roton. So we now see that the unit vector is a circle, because this would be, if that is a velocity, that would be a circular velocity. With A at right angles to the circle. So it would be pointing outward. It's in the X or inwards on the XY plane. And with the reactor pointing into the Z direction. Or I can put the alternative solution is that A always points in the same direction and into the Z direction, and R is pointing outwards. So, and I introduce here n omega 0, or this grave n. Basically, I'll put this the grave symbol on top of the n. It is just for me to when I work, that I know that I don't need to think of units there. So in anything that is unitless, I now going to follow I introduced my own convention to put a grave on there. I spent the other day trying to balance units where something was unitless. So and then we have the three-dimensional roton, which is a closed curve or wound up. So we've got here the unit velocity vector, which we can see is these would be spherical coordinates. The A vector is again a circle, or basically on one plane, and the R vector would be three-dimensional as well. And I introduce that omega 1 is Pn, where P is a prime integer. So that what would this? I just want to see where I am. Let me just go a bit forward so that you can see what they look like. These are the paths that they would follow. Basically, the path is obtained by integrating the velocity vector, which develops into this equation, and when I plot it, will look like this. Each curve, the length or the path length of that curve is equal to 2 pi. They are on sort of, if we look, the green one on the inside is with omega 1's 7 times faster than omega 0. And when you see we've got 1, 2, 3, 4, 5, 6, 7 sort of stars, edges to it. Like here we've got the 3 edges, and basically they get very circular with flattened poles. If we introduce these into a higher make the P to higher numbers. Okay, let's just go back to here. So that's okay, that we all said. Now, the energy of a 1D roton, this is where it becomes interesting now. That using from slide, we obtained that the action, we had this as the action, and basically why I'm showing this here is to because why I'm repeating this is that the omega 0, it is now n omega 0 here, which gives me the subtended angle, because it's faster. So basically, I now say that I can bring down that the action is epsilon 0 n a cross r. This is very much like the Poynting vector, which actually is 1 over mu e cross b. It should actually be b cross e. This would work, expands into epsilon dot n times r. R is, instead of having this as a unit length, I make it longer. In other words, if r increases, with the action increases with a square, and the action or rotary action increases proportionally with the frequency. And if we evaluate this based from the last slide, we get A equals L0. The A is scaling and the unit vector. And if we evaluate the norms of this, we basically reduce to hn times r squared, with r squared equals to 1. Let's fall it away, that being action, which is joules per second. So I must divide this by T0, which I then have H. The energy is equals to HF, which is the Planck energy equivalence. So basically, the rotary action that I have introduced would, and these rotary waves would explain the energy of a photon. Furthermore, the being rotary, I also have spin in this. So let's go back to this equation here. So basically, in this equation, I have things rotating here, which we can see, which is spin. And it is also following the energy of, as we know it, with the Planck energy equivalence. Now, the energy of a three-dimensional wave. Now, basically, the three-dimensional wave, I've chosen such that A looks exactly the same as the A here. We see that A equals R L0 A, X cos and plus Y sine. And this is exactly what I have here. And there was a previous one. So now to work it out, basically I've covered this. I need to define the path. I've shown this, but the radial distance from the origin, that this, in other words, from the center point here, develops into this equation, and basically, which is C over omega 1, which is, and we already had earlier omega 1 equals Pn omega 0. Therefore, that would be the radial distance. Now, we had the activation vector the same as discussed earlier. We already know what the the action is, which is in the bottom of this equation, HNR squared. And now I say that R, the I'm just thinking if I made a mistake. R, now R is greater than that. So basically, I say R, I never let A go over the geometric center. Therefore, R gray, the R gray has to be equal to C over P and W, which follows here, so that I then can say that the product Rn is equal to 1 over 2 pi, bringing that, if I look at that equation, I have HR n times R, which I've got here, replace it, so that I get basically the energy is H bar R over P over T0. So here we can see that the energy is proportional to R. If as R diminishes in size with P, the energy, let's go back to this equation, the energy of this, of this outer wave would be 7 or 3 times more than the blue one, or 7 times more than the middle one here. If I all unify them out onto the one, I must multiply by the P again. So if we, where we are, which basically means if those waves are all constant, we can see that it scales with R and not with frequency as with a photon. Now, how do I make particles with this? And this is where the space that we work in, instead of working in a real space, I'll start working in a complex space. And I'll also allow the load to be complex. And going back to those equations, we can find that if I make the load times e to the I alpha, which then requires, I then have 3 solutions for it, that I've got a complex speed of light, or real speed of light, and the same for minus alpha. So just showing all the conditions here. This makes it now very interesting, because now I can put into superposition.
Not even halfway through.
Pardon? I'll put into superposition a photon like that, the one-dimensional wave and the 3-dimensional wave. If I analyze this, this velocity c is real. The 3-dimensional wave's velocity is imaginary. I basically introduced this the scaling factor, the root sec theta here. This is actually the 2 solutions. I'm only showing one of the solutions here, and so this root here is basically we saw the factor r over 2 pi p. That, remember the 2 pi, that was because we had the h bar in there, and we note that the absolute velocity of the way that I've defined it here is the absolute velocity is c sine theta plus c cos theta. Okay, I need to square those. So it is the absolute velocity is equal to c, although it be part of it is imaginary or complex. The 3D roton, the energy content remains constant for all angles of phi. If we multiply the energy content, if I multiply A and phi, because basically it is the energy content is proportional to A squared, because R has got the A in there. So I've got the cos times sec, which is equal to 1, so it doesn't change. And for the 1D dimensional roton, the energy content varies with theta and is reactive. Here I use the electrical engineering terminology instead of imaginary energy. If we go back here, we can see if I multiply the e to the I pi over 4 gives squared gives me e to the I pi squared e to the, if I square these, e to the I pi over 2, which is equal to an I. So and I multiply by u, which is which makes us reactive. Here I've also got an I, but I multiply by an I up. This is a minus I times the I, which is 1. It could also be minus 1. It makes no difference, in my opinion, because we're basically we're working with the apparent energy. So the 1D and the 3D share a common activation vector. So if we look at these, okay, this one is scaled, but it is basically has the same physical orientation. And so the activation vector of the one-dimensional roton and the activation vector of the three-dimensional are common. I've put this, maybe this should be a minus, I don't know, but this makes more sense to me because when it is a lower energy term when I combine both of those together, because some of the imaginary parts will cancel out. But this I need to study further. Now, here's what does this come to? I've got the energy of the three-dimensional roton is h bar r over pt. That should be a sub 0. That is, I must mistake here on the slide. And the energy of the roton, that is because I've got this term in here, is equal to the energy of the 3D roton sine theta over cos theta. And the components of the velocity vector are u equals c sine theta, and for the three-dimensional one, it is complex or imaginary c cos theta. And if I square them and add them together, I get c squared minus, or rather this u theta is c squared minus u gamma squared, and the perceived energy is this. Now, we can do some fancy work here. We established the energy of the I notice also my e's are wrong here. They should all be in script. The energy of the combined roton is has this value, and I increase it by some or other dv, which means I have to increase these velocities. Therefore, the delta energy evaluates to this, which is just simply that minus that. If I do a series expansion on it, I get the delta, let's call it as delta E equals this term here. But we also know that now we apply Newton's second law of motion, and we know energy is force times distance. Therefore, if I do this in terms of Newton, I have a delta energy Newton is a mass, and the acceleration is du dt, and distance is u dt. And I now simply set this equal to that, and we basically works out that mi equals E, the energy of the three-dimensional photon, C over C squared over that. That is basically, if we look here, it is just cancelling out the du's cancel, the dt's cancel here, and one of the u's cancel there, which leaves the c over c squared to the power over 3 over 2. But if u gamma equals, or sub gamma equals 0, the above reduces to m0 c squared, and it trivially follows that the energy is m0 c squared over 1 minus v squared over c squared. So basically, I've got Einstein's relativity here in a Cartesian coordinate system, using the energies of the rotons as I've done there. This is as far as I've got I want to go today. But basically, what my concluding summary, that Maxwellian dynamics describe protons, or rather as solitons. I'm hinting that the electrostatic charge, that means the proton-electron interaction, is different to the electric charge that drives industry. Rotons as photons explains Planck's equals hf. Rotons explains Newton's first law of motion in terms of a propagation of a wave. Nobody has said why Newton's first law of motion is true, and this is actually how this study all started many years ago. I said momentum has to be a wave, that first, because a wave is the only mathematical description we have for something to move at a constant velocity. I showed that rotons explain the origin of inertial mass. So I haven't got gravitational mass here. I explained inertial mass. I haven't used a no Higgs field here. Rotons explain equals mc squared and the relativistic momentum. I must also say that everything that presented here does not contradict experience. Although that I have now introduced a complex dimensions into the space that we live, and this is also not something new. Physicists always use complex numbers. Anyway, let's leave it at that. That's my last slide for today, and let's have a discussion. And let me stop share here. Okay. So it was rather difficult for me to explain all of this, because this is all rather new, and I still have to think about it every time that I work with it. I will answer Mike Horner's question, where's my hand waving? And my hand waving was basically introducing that in the one set of equations, the root of the second of an angle. That is, in all of this. The rest is all, that was the only sort of introduction or something that I introduced to obtain the result that I wanted. Okay.
Can you say that again, what your hand waving was? I didn't catch the words.
My hand waving, I'll show it to you. Let me just share again. My hand waving is on this slide here. Is basically introducing the square root of the second theta and the square root r over 2 pi p. Basically, with those are the factors that I have to put in to obtain the result that I wanted. So. Okay.
I have a suggestion. If you look at the evolution of the mathematics you're using, they're following the sort of obvious things. You begin with a Euclidean space. First of all, you just got one dimension. Then you got another dimension. Then you got a third dimension. Then you've got direction. And then you've got rotation. And then finally you get rotation in a circular way, right? So presumably the formalisms that, for example, Peter Rowlands uses, they follow the same sort of evolution. So I think I remember a few months ago seeing a paper on gyro vectors. I wondered if the gyro vectors might actually be very similar to your rotation idea.
Gyro vectors. I must look up what's in there. Basically, I want to introduce what I call fluxors, because the way that I am showing this does not describe a magnetic field of a moving electron, because I've got the let me go back to let me share the screen again. In developing E equals mc squared, I put a propeller wave, or this one-dimensional roton, which is also a photon, into the combine that or in superposition with a three-dimensional wave, which propagates in complex space or imaginary space. Now, we know that a moving electron has got a magnetic field around it, similar to the electric field of a current. So there is a circular around the electron beam, I've got a circular magnetic field. Now, if I look at this, I don't see a sense of a circular field. But what I can do without changing anything here is to move the activation vector, that's the one which is double, instead of it rotating on the end, on the axes, I can let me see, if I basically I can drop that point to the I can let that vector start at the beginning of say of this I'm doing it, yeah. I drop it down onto here so that it basically it would it be at the end of an arm. It would look like a hockey stick. So if I rotate the hockey stick, the puck, or what you call the head of the hockey stick, would then follow on this path here, and that could then be a magnetic field, you know, the circular magnetic field. I need to draw it out. I should have done this as here, and that is what I would call a fluxor, and that would make show the that would then, instead of here of these two pointing outward, then this one would, if I extend it onto this rotating path here, would also be basically be moving along a circular path. Yeah. But anyway, that is work that I still need to do.
I was hoping that you could take a look at this relatively recent work on gyro vectors and get some inspiration, or
yeah, no, let me just see about Google gyro vectors if it comes up. Have you got a link? Or have you?
I can dig out something.
Yeah. Gyro vector space. Okay, that's in Mathematica here. Okay, okay. I will look at that. Okay, that's.
So in a way, since most of the argument is around energy, you're sort of always assuming that the conservation still applies. And my sense is that we don't have a particularly good handle on the concept of energy when we move out of dealing with ordinary matter and waves or particles and so on. So when we get into, you know, more complicated things like life, then becomes clear that energy is not just the power to move something in the physical space, you know, and it's got different qualities and so on and so on. So it's a sort of more mysterious notion, which is maybe creeping into some of these arguments, you know.
Correct. I thought a lot about it. You know, life energy is something that I think of a lot as well. It's basically, you know, at the moment, the way that I've done it, this would all be using the electromagnetic domain. Now, could there be a parallel domain with life energy? I don't know. Or is life energy a form of electromagnetics? Which it might be, because all our, you know, the medics use electromagnetics to look at our, what do they call them, these graphs for on the heart, and then your brain scans and so on. So there's a lot of electricity flowing in our body anyway, which people can measure. What would interest Peter in this, which will be the next talk, is I will start making zero potent, or basically combining these into zero potent entities which cannot be destroyed. So I have matter, antimatter, which never can be destroyed. So basically, that will be my third talk, and that will also include start going into field theory, so that we can have, the particle-light duality. So, Mike, your point on the gyro vectors are noted.
How long have you been working on all this, Anton?
Look, many years. I basically, it started when I was in the UAE, and I was driving or being driven with an Indian engineer from Abu Dhabi to Dubai on a hot summer's day, and we were sitting in the back of the car, and I just asked him, "What is momentum?" And then basically that, after that discussion, I came to the conclusion that momentum must be a wave, and if you look at my earlier works and presentations to AMPA, I had three-dimensional waves. I've developed an algebra, which you can actually see on the neophysics side to do that. And then basically the breakthrough was earlier this year when I wrote down those three vector algebraic equations, which, by the way, also solve the Faraday paradox. That is that disk, when you spin a disk in a magnetic field, that a unipolar generator. You can see those in those equations as well. So that's there, which gives me rise to the fact that the electric current is not what we think it is.
Didn't Heaviside have some things to say about this when he tried to investigate how all the electrical things happened, and it wasn't all going through the middle of the cable and stuff like that? That's a big rat hole to go down. Sorry about that.
Let me, I'm just preparing something here, and I'm going to. Okay, let me share the screen again. Okay, here we're looking at a picture that I've taken out of Van der Graaf's paper, which was published in 35 or 33 or somewhere, when he produced the Van der Graaf generator. And I really have to smile at this paper. This guy's working at MIT, and it talks about spraying on electricity at these points, that the one thing, so anyway, I like, this is a thought experiment that I want you to think about. If I have a particle generator that shoots out high energy charged particles at ground potential, so from here to here, the kinetic energy of particle P remains the same. It is then accelerated between A and B, which is, and this V1 equals to V2, by the way. So, so here it gets accelerated. Getting accelerated, so it's got a higher energy, kinetic energy at point B, the particle, than what it entered at point A. That means the battery V1 must have delivered some energy, which means if it delivers energy to here, there is a current flowing from A to B. But I can, from B to C, because the potential, they are exactly the same here, so there is no kinetic energy difference there. And then from C to D, it gets deaccelerated because now the polarity is opposite to A to B. So I'm charged, basically, I'm putting current back into V2. So when this particle exits D, the total energy in the system hasn't changed, but I have now transferred energy from V1 into V2. But this particle, I don't need to shoot down one particle, I can shoot down continuously. You know, if I take this to CERN and put this into the particle beam, I will have a continuous current flowing from A to B, and a continuous current flowing in C to D. Now, in other words, there cannot be electrons, because where do all these electrons come from and where do they go to? You know, so Albrecht, you worked at, it was particle accelerators at DZ. Ask your, you know, discuss it there if you still got contact.
Yeah, I've no contact any longer, but of course we have accelerated electrons, but that is a complicated system, also with partial fields. But these fields are changed by some high frequency generators, so that there is always an accelerator from one part of the of this way to the next one.
Yeah,
this
correct.
is static, what you have shown here. That is a different story, I think.
Yeah. No, but this, for me, this proves that the concept that electrons are the charge carriers for electric current is completely wrong, because basically this thought experiment here proves this to me. So anyway, that's that's what I have to say about.
Anton, can I have a picture of that thought experiment so I can copy it off the screen?
It's in the, if you go, it's in the paper, it's in the appendix of the paper. If you go onto the website, and
On your first paper.
Yeah, pardon? On the website neophysics.org, on my latest paper, it's on page 33.
Very good, thanks.
Yeah.
So it's your own stuff.
Pardon?
I see. I thought it was from somebody else, but it's your own thing. Good, great.
No, that's my own thing there.
I'll try to understand
it. Anton, a reference back to ANPA days.
Mm-hmm.
Pierre Noyes had a model of a particle. He says the word particle, and you know, whatever it is, a photon or whatever, he says is a carrier for the concepts or the attributes of that. So if you say that experiment is some change in energy, and maybe there's something to do with mass and so on, So his idea is that the word particle is, in a sense, a sort of a label for a concept which is hidden behind the word itself. And you can go one level back, and then you say, these are the attributes of this particular particle. And as you know, it's usually, mass, charge, and all those things, right? So I'm not sure that I can follow you in that very last step. It's a nicely drawn diagram. But when you say, therefore, it must be a particle, I'm sorry, I can't buy that. It could just as well be a wave.
No, what I'm saying is that the particle being accelerated needs energy, and the energy is supplied by the battery, and there's electric current flowing. Now, the definition for electric current is electrons migrating, which is this experiment shows that it isn't. If I look at the Van der Graaf generator, there is something that isn't I haven't found in the literature, is if you take a capacitor and you charge it to, say, a capacitor of 2 plates, just 2 metal plates with an air gap of, say, 10 millimeters, and you charge it to 100 kilovolts. There is a force that will try and pull these 2 plates together. But you can now pull these 2 plates apart. So if they were now 10 millimeters apart and you now move them to 20 millimeters, you would have doubled the voltage, because the work that you're putting in to pull these capacitors apart increases the voltage. And this is basically how I see the Van der Graaf generator working. Because we looked at it earlier, which then increases, so there is this conversion of mechanical energy into electrical energy. And this is something that we need to find. Now, what is a particle? That's, it is basically, in my opinion, we are all just manifestations of waves, that would explain memory as well. We attribute memory to firing of neurons and having these fancy neuron circuits there. I say the neurons are basically there to measure the waves, because once I've got a wave trapped in my brain, it stays there forever. Therefore, I don't forget anything, or not supposed to forget anything. We only forget because we don't know how to read that wave anymore, or we put that wave somewhere where we don't fire neurons. So I don't see memory as or the mechanical model of the brain of being a computer with neurons. It doesn't hold with me, that I see the permanence of waves there.
Okay, your gods are waves, other people's gods are particles, other people's gods of complicated, weird things in quaternions. Right, Peter?
Perhaps I can make another proposal for particles. That's my view, that particles are collections of charges, either electric charges or charges of the strong force. And if they are combined and put to a place, then we have a unit which behaves like a particle. I do not see waves as the origin. If you have such a collection or what is this setup of charges in a specific way, and you have rotation of charges, which you have in a particle which has a magnetic field, for instance, then these rotating charges cause a wave outside. So I would see the wave as a secondary effect. The primary effect is the charge. That is a way to look at it. So it's my way to look at it.
So, unanimous disapproval or approval, I'm not sure.
I think we've all got a look. The thing is, the next part, is basically what is a field around the particle. You said the field, is charged, but how do you describe that field? It's
Quantum mechanics. That's my understanding. That's the only thing, or one of the few things where I follow quantum mechanics. Fields are, in the view of quantum mechanics, realized by the exchange of exchange particles. These are particles which are massless and move at the speed of light. And when such an exchange particle goes from one charge to the other one, it transfers a momentum, either a repelling momentum or an attracting momentum. And I think this is a good way to describe field. By my work up to now, I did not need any other properties of a field like just this view that it is a collection of exchange particles, yeah, as I said.
It's how does a particle know where the other particle is? Take a multi-party system that exchanges particles in all directions. That's where I don't, where my thinking breaks down. Is
no. Why is that a problem? And of course, it is seen in the way that charge emits exchange particles to all directions all the time, which means, and that is some thing one has to take into account, on that level, a violation of the conservation of energy. That has to be accepted for this picture, but otherwise, I do not see any disadvantage of this picture of a field. At least in the areas where I work, this was always sufficient to describe a field. And it's, for instance, very useful. We know from special relativity that in motion, fields contract. And if you have this picture, this understanding of a field, then it's very simple to show that fields do contract in exactly the way as it is described by the Lorentz transformation. That follows from this picture. And I think this is a good argument that this is usable, at least a usable view of a field.
But that means that the particle has got infinite energy.
Yeah, and energy, what I said, energy is not conserved. Yeah. And I think energy is conserved. I have a particle model. I thought here's a place now to explain this.
Yeah, no, I know your particle model.
I have a particle model which is built by, for instance, two charges of strong field. And the setup of this particle is the argument that we have conservation of energy, but we have it on the level of a particle, and of course on the levels above a particle, but not on the level below the particle. That is something we have to accept with this picture, that below the level of a full particle, there is no energy conservation. That is what we have to accept.
Yeah. Okay, we can discuss. Maybe Albrecht, you might want to make a presentation here sometime and discuss this in more detail.
I have explained this picture many times.
Yeah,
in the PIRT meetings and so on. Yeah. I could do it again if you want it.
I know that your presentation. I've seen them at the Vigier, and anyway. So if you've got some more developments on this, we can present them here. No, but I'm actually I'm actually the direction that I'm developing is we've got accelerating forces which are basically which add energy to a particle, like in the particle accelerators of CERN, and then if a particle is a wave, and if the space or the ether that this wave is moving in, we know that it bends around the gravity field. But what I'm suggesting is that gravity is basically the particle wanting to move into a higher gravity field because the speed of light is lower there. If I work in a three-dimensional Cartesian coordinates and not in space-time, I need to bend my space differently to what Einstein bends it. Einstein bends the physical space to give gravity, but I bend the speed of light. So basically, I go away from the constancy of light into a varying speed of light, and that will cause the light to go into a space where the speed of light is lower, which is a higher energy field, and also or electric field, which gives you the electric repulsion or attraction. I will show that in a later in my next presentation, or actually be. Therefore, we have basically, as I said, we have accelerating fields like in particle accelerators, but gravitational fields, the energy to move towards the other body comes from within the particle itself. Therefore, the energy does not increase, and basically we'll have the effect of that would be that inertial mass would diminish as we get into higher gravity fields. But that is for later. But let's try and get back to the original discussion. Oh, Richard Amoroso is a bit late. He just joined us. Nina, have you got something to say? You're very quiet. Your microphone is off. I can't hear.
Me?
No, Nina.
Oh, Nina.
Yeah.
What has Peter got to say?
Moment, I was going to ask Anton, do you have a direct connection between the mass of an electron and the electric charge?
Basically, yes. Would it be? You'll have to wait for the next talk. Can we answer that with the next talk? When I will bring in particle wave duality there, and the particle wave duality will basically, the duality part is what causes a field. So, the mass is the energy. So if I take the electron as a fundamental or as a quantum part, the smallest particle that could exist, then yes, the energy, they would. Yeah, it would be constant, but anyway, let's wait till I've got that work prepared.
Okay, we'll wait till then.
Yeah, it's I can basically, once I've got this written up, I can send it to you, because you should be very interested in it, because that will deal with null potency. You know, I will develop a the whole universe is null potency, and the interesting part of that is what will come out of it is that and also why the gravity is so much smaller than the electric field. You know, that's it's got to do with I showed the load today at 45 degrees, you know, pi over 4. If you make it pi over 4 plus a small delta, and then if you multiply these complex numbers together, you find that you'll have a huge imaginary number, which will be your electric attraction, and a very small real number, which would be your gravitational attraction. This is so basically both will come out of these, the gravity and the electric charge will come out of the same equations. But that is what I want to do in the next talk then, or the talk beyond that. And then I already have shown, if you look at my work at, which is in the AMPA proceedings, a bit difficult to read because it hasn't been English edited, so there's a lot of grammatic mistakes in it. And it's also in one of the Vigier papers. I actually show that I can make planets, the precession of Mercury, I can do in a Cartesian system. And the best part is that I can do the time dilation of clocks using the Bohr model with the way that I'm going. This is basically, I developed that part before, but now I'm developing it from the Maxwell equations into the field equations, into the interactions. And that is basically based on the fact that if two bodies attract each other with a gravitational force or electric force, there is no energy increase as these bodies speed up, which is contrary to what we believe, because basically that's your being a wave. I just rearrange, the particle rearranges the wave to move faster. Whereas in a particle accelerator, we add energy to the wave to move faster. Anyway, so shall we call it a day?
Thanks again for arranging everything. You have a new date for the next one?
Yes, thank you for reminding me. The new date is the 7th of January, but that is not me talking, it is Nina presenting. Nina, I forgot your title, I put it into it. Can you tell us what the title is? Microphone.
The Schrödinger equation is a condition of the stability of the quantum particle. About Schrödinger equation.
So, looking forward to that. I think we can read about, you know, if you, those papers you've already published something in that respect, I think in the Vigier conferences and in the AMPA, haven't you?
Only conference, but I'm prepared the next.
The follow-up on that. So, okay. So. And anyway, you can, my paper and the is on the website. You know, my second paper for continuity, because I sent it to somebody else, I've included the first paper in the part 1, and then the part 2 is what we discussed today. The slides that we had today you will find on the website. If you go into the talks and click on the link for this talk, you'll find a button called PDF, and then you can download the slides.
Can you tell me what time on January 7? Will it be 7 p.m.?
It'll be the same again. Is this time okay, or do we want it earlier?
Fine.
It's a good compromise, I think.
Correct. Okay, then I wish you guys all a happy Christmas and a good New Year. And we'll see you in the new year then. Enjoy the celebrations. Don't drink too much.
You
Thank
too.
you.
Thank you.
Well,
Your effort
You too.
No.
to understand it. I'll be working on to see what it's all about. Thank you.
Thank you.
Okay, fine. Let me stop this here. Okay, then. Okay, then let's close this down. Richard, show yourself. Can we see him? No. Okay,
Good.
let's.
Good to see you, Anton.
Okay, fine. Bye for now.
Bye. Bye, everybody.